Modern forestry is often perceived through the lens of conservation, but historically it is a centuries-old industrial discipline built on mass extraction and calculated management. In 1938, the forester Richard Heskay formalized the core of this discipline, silviculture, defining it as the science and art of producing and tending a forest. Unlike general ecology, which studies natural systems exactly as they are, silviculture is interventionist. It actively manipulates biological systems to achieve specific commercial or protective goals. To execute these goals, the forester must break the forest down into a manageable operational unit, the stand. A stand is an aggregation of trees that are uniform in their species composition, age, and physical arrangement. The stand is to a forester what a cell is to a biologist. It is the lowest divisible unit of the forest that can be mathematically engineered for yield. An unmanaged old-growth forest is a dense, chaotic network of competing species. But by contrast, a managed stand, exactly like this even-aged timber plantation, is built on strict architectural order. Unmanaged ecosystems naturally maximize biodiversity and resilience against disease. Managed stands deliberately sacrifice that diversity to optimize for a highly targeted economic output. To achieve that optimal output, a forester must do two things: quantitatively measure the biological productivity of the site and actively hijack the stand's natural regeneration dynamics. Before a single tree is felled or a sapling planted, the forester must deduce the exact mathematical and biological baselines hidden in the soil beneath them. Every stand's productivity is bound by three site factors: climatic variables like rainfall, biotic variables like grazing animals and fungi, and edaphic variables, which concern the physical soil itself. The edaphic variables dictate exactly what can survive on a given plot. A soil's pH levels, drainage patterns, and nutrient-holding capacity act as strict biological filters for tree species. These environmental filters define the parameters of regeneration ecology. Beneath the forest floor lies the soil seed bank, a subterranean reservoir of viable genetic material, lying dormant and waiting for a catalyst. This animation illustrates a transient seed bank. Teak seeds remain viable for only weeks, decaying rapidly without ideal conditions. Contrast this with long-term persistent pine seeds. These survive underground for centuries, requiring a severe disturbance, like fire, to break dormancy and trigger explosive growth. Knowing whether a stand relies on a transient or persistent seed bank dictates exactly when and how aggressively the forester must harvest the existing trees to trigger the next generation. To calculate how fast that next generation will grow, foresters rely on the site index, the single most practical metric of a location's biological productivity. This chart breaks down the site index, calculating the height of dominant trees at a specific reference age using the Schumacher equation. This base age varies: 10 years for fast-growing biomass or 100 years for slow-growing timber. Height growth remains constant regardless of crowding, providing a stable baseline. Next, foresters manage crowding using Reinecke's stand density index. Hitting this maximum boundary triggers mandatory self-thinning. The site cannot sustain the biomass, and weaker trees die off. To prevent this wasted mortality, foresters use a final spatial metric, the crown competition factor, or CCF. CCF measures maximum crown areas divided by total area, shown here as expanding canopies. The critical threshold hits as the counter pushes past 100%. The canopies intersect, actively competing for sunlight and stunting growth. The math dictates intervention. These mathematical models remove the guesswork. The equations explicitly dictate exactly when a stand is choking itself and must be physically cut to maintain yield. That physical intervention is executed through silvicultural systems. These are specific harvesting methods designed to manage density and force regeneration. The most aggressive intervention is the clear felling system. An entire block of trees is removed in a single operation, leaving the site exposed. This is reserved for fast-growing, light-demanding pioneer species like eucalyptus, requiring full sun to form a new stand. Another method of aggressive turnover is the coppice system. Instead of planting new seeds, the existing stems are severed completely at ground level. This severe cut removes the tree's tentacle inhibitors, allowing auxin to stimulate dormant buds. As seen here, fresh shoots rapidly sprout directly from the remaining stump, utilizing the previously established root system. Both clear felling and coppicing operate on the same principle. They instantly reset the stand density index to 0, maximizing available light and forcing an explosive crop. High-density turnover doesn't work for fragile species that cannot survive total exposure to harsh sunlight. For these, foresters deploy the shelterwood system. This deliberate multi-stage process removes only a fraction of the upper canopy. The resulting dappled shadow protects delicate transient seeds of shade-tolerant species. Once young saplings establish deep root systems, the remaining mature trees are removed, handing full sunlight to the new generation. The most intricate method is the selection system, designed to maintain a permanent, uneven-aged forest structure. Instead of clearing large tracts, the forester targets single, mature individual trees. Removing one massive canopy creates a precise microgap, letting in a localized beam of sunlight to trigger a continuous cycle of natural regeneration. This delicate system is mandatory in fragile environments, like the steep slopes of the Himalayas shown here. Species like fir, spruce, and deodar require continuous ecological cover to survive and prevent soil erosion. By calculating exactly which trees to cut, the forester manipulates the atmospheric variables above ground to awaken the specific seed bank waiting in the soil below. Silviculture is far more rigorous than simple tree planting. It is the calculated hijacking of natural biological succession. Whether a stand is managed for an 80-year rotation of sal timber or a 10-year block of paper pulp, the biological constraints of site index and crown competition remain absolute. Today, these foundational mathematical principles are now being scaled across millions of hectares of land through the emerging field of precision silviculture. Remote sensing and aerial LiDAR are replacing manual measurements, scanning topographies to calculate precise site indices instantaneously. Artificial intelligence and machine learning algorithms process the resulting data, analyzing thousands of overlapping crowns to predict tree-specific thinning schedules. Drones are even deploying seed bombs directly into targeted canopy gaps, executing spatial regeneration with pinpoint accuracy. The forest is no longer an unpredictable wilderness left to chance. Through the rigorous application of silviculture, it is a calculable, highly engineered architecture of yield.